Hello everyone, I'm Hyung Wan Do from Professor Karl Berggren's group, and today I'll be giving a talk on Ising-model-based simulation of block copolymer self-assembly in 2D post-lattice. In our group, we have been studying graphoepitaxy of PS-PDMS on 2D post-lattice templates fabricated by high-resolution E-beam lithography. We have previously demonstrated complex circuit-relevant patterns using PDMS functionalized HSQ posts as shown on the left. Using PS functionalized HSQ posts or sacrificial PMMA posts, we have demonstrated three-dimensional bilayer mesh structures and whole arrays with different shapes and geometries as shown on the right. In all of these previous work, the resulting morphologies were modeled by well-established self-consistent field theory simulations or SCFT simulations. But we wanted to design a simpler model designed specifically for the 2D post-lattice setup that enables fast simulation over large template array. So in this work, we developed a new Ising model-based simulation that agrees very well with previously reported experimental and simulation results. The simulation technique will have applications in block copolymer pattern prediction as well as template design. Moreover, we expect the simulation to be useful for other interesting applications beyond just lithography, as will be discussed later in the talk. Before we go into detail, I have to mention why we chose the Ising model in particular, other than different types of models. In block copolymer self-assembly, we know that as annealing time is increased, the correlation length and grain size of the block copolymer is also increased. This is a simulation result demonstrating phase transition behavior in Ising states with ferromagnetic interactions. As the number of simulation steps is increased, the interacting Ising states reach phase transition, and correlation length and grain size are also increased. We can see a similarity between the two resulting patterns, so we thought maybe it is possible to apply the Ising model to block copolymer self-assembly. The Ising model is a mathematical model of interacting magnetic spins originally invented to explain ferromagnetism and phase transitions in statistical mechanics. The Ising states can take values +1 for spin up, -1 for spin down, and can interact only with their nearest neighbor states. The Hamiltonian of a configuration sigma is given by the equation below. The first sum involving J corresponds to energy due to individual nearest neighbor interaction. The second sum involving lowercase h corresponds to energy due to individual states. Assuming that j's and h's are independent of lattice location, they can be taken out of the sum. To apply the Ising model to block copolymer self-assembly, we have to first design an Ising lattice. Without any templating, PS-PDMS forms a typical fingerprint pattern with equilibrium periodicity L0 equal to 39 nanometers. We use a PDMS functionalized HSQ post template with horizontal and vertical pitch of L0 to guide the self-assembly process. After block copolymer self-assembly, the resulting PDMS structures can only be aligned horizontally or vertically due to commensurability. And here we define the Ising states based on the connectivity between two adjacent pair of posts. When two adjacent pair of posts were connected by a PDMS structure, as shown on the bottom inset, the Ising state was defined as +1. When two adjacent pair of posts were not connected by a PDMS structure, as shown on the top inset, the Ising state was defined as -1. This assignment ensured one-to-one mapping between a block copolymer pattern and its corresponding binary state array. We measured the distribution of +1 and -1 states to be close to 50-50, and correlation between adjacent states to be close to -1, indicating anti-ferromagnetic interactions or negative value of J. To summarize the Ising lattice setup, we first have the 2D post-lattice template. The Ising states were defined at the center of each pair of adjacent posts. Then there must be interactions between nearest neighbor states, because nearest neighbor states in this setup are physically connected to each other at the post location through PS or PDMS domain. This mapping may not seem intuitive at first, so as an example, suppose we want to convert the block copolymer pattern on the right into a binary state array on the left. In the first column, the three states are all connected by a PDMS structure, so they're assigned +1s. In the second column, all 4 states are not connected by a PDMS structure, so they're assigned -1s. In the third column, all 3 states are connected, so they're assigned +1s. In the fourth column, the top 3 states are not connected, so they're assigned -1s, but the bottom state is connected, so it is assigned a +1. After finishing the conversion, we can check that any binary state array can be uniquely mapped to a block copolymer pattern, and any block copolymer pattern can be uniquely mapped to a binary state array. Finally, we can check that antiferromagnetic interactions, or negative value of J, indeed make sense, because antiferromagnetic ground state configuration consisting of alternating +1 and -1 states map to parallel PDMS lines which are energetically favorable. On the other hand, ferromagnetic ground state configuration consisting of only +1s map to a PDMS grid, and ferromagnetic ground state configuration consisting of only -1s map to no PDMS line formation, and both structures are energetically unfavorable. Next, to perform Ising model simulations, we have to know the relative value of H compared to J. We already know that J is negative due to antiferromagnetic interactions. Consider the following band structure consisting of 1 center state and its 4 nearest neighbor states. To calculate the Ising Hamiltonian, we can first convert the pattern into a corresponding binary state array. Then we can calculate the Ising Hamiltonian. In the first term, there are 4 interactions, 1 between 2 +1 states and 3 between a +1 and -1 states. These sum up to 2J. In the second sum, there are 5 states which sum up to H. So the Ising Hamiltonian H1 is 2J plus H. From experimental data, we can measure the distribution of center state given this specific 4 neighboring state configuration. When only one of the 4 neighboring states was +1, 96.7% of center state was +1. We can repeat the same process for the case where the center state is now inverted from +1 to -1, while the 4 neighbor states remain unchanged. The Ising Hamiltonian H2 is -2J plus 3H, and given this specific 4 neighboring state configuration, 3.3% of center state was set to -1. We know that the left configuration is observed with much higher probability, so H1 must be less than H2. This inequality simplifies to 2J less than H. In the previous slide, we examined the case where only one of the 4 neighboring states was +1, but we can repeat the same process for different neighboring state configurations. In case 1, all 4 neighboring states are +1s. In case 2, 3 of the 4 neighboring states are +1s, and so on. For each case, the SEM images show the center state with higher observation probability. We can get one inequality for each case, and the 5 inequalities simplify to H between 2J and 0. For simplicity, we chose H equal to J for simulations, but any value of H between 2J and 0 will give the same simulation result. Finally, we want to implement boundary conditions by fixing specific states to +1s and -1s and see the effect in the simulation. To set a specific state to +1, we placed a double post to induce PDMS structure formation. If we draw the Ising states defined at the center of each pair of adjacent posts, the 2 states colored in red are fixed to +1 states. In addition, from experimental data, we observed that the 6 states that are adjacent to the double posts are also affected by the templating effect of double posts. So 8 states in total will be affected by the templating effect of double posts, and their fixed binary states are shown here. The corresponding PDMS structure is a straight line around the double post, meaning that T-junctions, bends, or terminations cannot be formed at the double post. Now we can perform Ising model-based simulations. This is one of the target templates we used for simulation. The first step is to generate random initial solution, where the states around the double posts are fixed as explained in the previous slide, while the other remaining states are randomly chosen between +1 and -1 states. For easier visualization, horizontal and vertical structures are colored red and blue and red, while other morphologies such as bands, terminations, or T-junctions are colored gray. For each iteration, we chose a random state sigma. Then the Hamiltonian of the current configuration and the Hamiltonian of a new configuration where the chosen state is inverted were calculated. If the new Hamiltonian involving inverted state is lower, then the chosen state was inverted for the next iteration step. Otherwise, the chosen state was still inverted with probability p, which is a function of the difference between the two Hamiltonians and a simulation parameter t, which goes to 0 as the simulation progresses. This step was required to escape from local minimum. Now this is a video demonstrating the simulation results after different number of iteration steps. After a few thousand iteration steps, we can already start to see an somewhat ordered pattern formation. And after a few tens of thousands of iteration steps, the morphology reaches equilibrium. And equilibrium has been reached. This is the minimum Hamiltonian configuration, which agrees with SCFT simulation results. We have the same figure in grayscale, which agrees very well with experimental data. We have shown that Ising model-based simulations can be used for block copolymer pattern prediction and block copolymer lithography. Another interesting application for the Ising model is Ising model-based computation. It is known that universal computation can be encoded into ground states of Ising lattices by designing specific Hamiltonians. For example, a buffer can be constructed in antiferromagnetic Ising states by simply connecting 3 Ising states. If the input is fixed to +1 or upspin, the output in minimum Hamiltonian configuration is also set to +1. If the input is set to -1 or downspin, the output in minimum Hamiltonian configuration is also set to -1. So this design acts as a buffer. Now we will demonstrate the buffer and inverter using block copolymer self-assembly. Consider the following 2 post arrays. After block copolymer self-assembly, we know that a boundary will form because of the double posts. And inside the boundary, the PDMS structures will be aligned either vertically or horizontally in minimum free energy configuration. The experimental results agree with our prediction, and SCFT simulation results also agree with our experimental results. Now consider the same post array with additional double posts to define inputs. Inside the boundary, we defined an input state and an output state. In the top case, the input is fixed to +1 due to vertical double posts, and output has not been determined yet. In the bottom case, the input is fixed to -1 because it is adjacent to a horizontal double post, and output has not been determined yet. After block copolymer self-assembly, the output is set to +1 when input is +1, and the output is set to -1 when input is -1. Since the output state is set equal to the input state, this design acts as a buffer. Now we can repeat this. We can simply change the buffer into an inverter by choosing a different state to be the output. Here, the output for the inverter is adjacent to the output for the buffer. Since the 2 states are adjacent to each other, they must have different signs in minimum Hamiltonian configuration. So the output is set to -1 when input is +1, and output is set to +1 when input is -1. So we now have an inverter. In conclusion, we demonstrated an Ising lattice setup in block copolymer self-assembly and reproduced previously reported experimental and SCFT simulation results. Also, we demonstrated an inverter, proof of concept inverter and buffer using block copolymer self-assembly. Our next step is to perform universal computation by building different types of gates, such as AND gate, OR gate, or 3-input majority voting logic gate. We already have designs based on the Ising model simulations, and we are currently doing more experiments. Other than universal computation, it is known that combinatorial optimization problems, such as the traveling salesman problem, can be mapped to the Ising model. So our long-term vision, ultimate vision, is to use block copolymer self-assembly to solve complex optimization problems. That's the end of my talk, and thank you for your attention.